We are looking at Part C of the June 2022 Chemistry Regents exam. Part C is at the end of the test. You're talking 20 questions. You're talking all short answer type questions, questions coming from different areas of the course. It's the end of the test. Students are getting tired. Remember that it's tough to even pass this test, so you want to try with every part to get as many of the questions correct as you can. Let's get started. Again, we have reading passages and questions that may or may not go along with those reading passages. Let me just move this up. So here we're going to have question 66 through 70. We have information along with a balanced equation. Don't blow this off because this might actually be something in here that you need to answer one of these questions. Read it over, pause the video, try to answer the questions yourself, and then come on back and see how you did. We're going to just keep rocking and rolling. In 66, we want to show a numerical setup for calculating the number of moles of oxygen gas required for the average person per day. And you're even given the gram formula mass. You don't even have to calculate that. Now, for moles, when you have the gram formula mass, let's flip over to reference table T in case you don't know where this particular formula is. And here's reference table T. Now we need to go up. And right here, you can see we need the mass. We're going to divide by that gram formula mass that was given. We're only doing numerical setup. Literally at that point, you can stop. You don't have to calculate the answer. And if you only provide the answer, you would actually get this question wrong. Numerical setup means you're plugging the numbers in. We need then the mass. So moles is equal to mass divided by gram formula mass. I have the gram formula mass as the 32, and the average person on board of the International Space Station required 840 grams of oxygen per day. So that's coming from up here. So literally all we're dealing with is 840 divided by 32. This is what you want to have on your answer sheet, and you're ready to go. You don't have to worry about units here, but when you get stuck and you're not sure maybe how to set up a question, it might be important to put the units down. It won't hurt you if you do, but you don't need to because it says literally numerical setup. All right, let's look at 67 now. State the change in oxidation number for oxygen during this electrolysis reaction represented by the equation. All right, our equation's up here. Now, remember when you have an element alone, such as O2, the oxidation number is 0, right? It's only sharing with another oxygen atom. There aren't other elements involved. Oxygen number for oxygen here in water is a -2. Now you can look up the oxidation number for oxygen on the reference table, specifically the periodic table. It's going to be shown in the upper right-hand corner. Of course, you have an oxidation number of -2 for oxygen and H2O because oxygen is pulling electrons or sharing with hydrogen, but pulling them towards itself, and each of the hydrogen atoms would have been a +1. So the change in oxidation number literally is a -2 to 0. For 68, it says determine the number of moles of oxygen vented into the cabin when 120 moles of water undergoes electrolysis. All right, so now we have a stoichiometric problem. Again, let me erase all of this. What I like to do with my students, this is what we call a mole-mole problem. You're given moles, you're solving for moles. The moles you're solving for, you got to go back to the balanced equation. Here's my X, and I have 120 moles of water to start. Now what we're going to do is we need the ratio of water to oxygen, and we use the coefficients, the numbers in front of the balanced equation. That's going to do it for us. So here we have 2, and here it's understood we have a 1. So literally we have a ratio of 120 over 2 is equal to x over 1. Well, 120 divided by 2 is 60. So our answer here is 60 moles. So far, so good. Let's go to 69. Okay, 69, we're going to do percent composition by mass of hydrogen in water. We have our formula for water as H2O. When we're dealing with percents, I'll put it down here, right? We're going to have the part over the whole thing times 100. This equation is found on the reference table. Don't forget about the 100. I strongly suggest that when you're working with the math problems, you put the equation down on the test paper. And we're determining here, so that means that they want the actual answer. All right, in order to figure out the mass here, we need to go to the periodic table. And what you're going to find is you need the gram formula mass for hydrogen, which of course is 1, and the gram formula mass for oxygen, which is going to be listed as 15.999, something like that. Just round it to the whole numbers, it's 16. So literally, the whole here on the bottom, because I have a formula, compound formula, is just the gram formula mass for water. And then the part, since it's mass of hydrogen in water, that's going to be the contribution for the part. I like to show my students, let's just calculate the gram formula mass. We'll get the whole thing, and then the part will pull from this line for hydrogen. Alrighty, so I have 2 hydrogen atoms in every 1 water molecule and 1 oxygen. I'm going to multiply hydrogen by 1. That's the gram formula mass on the periodic table. And oxygen 16. When I do this, I get a 2 and I get a 16. My gram formula mass for water is 18. So that's the whole that goes in the bottom. And the part is the hydrogen alone, which is the 2 times 100. And when you put that in your calculator, and you calculate your answer, it's going to be 11%. Let's move to 70. All right, for 70, we're balancing the equation between lithium hydroxide and carbon dioxide in the answer booklet. I wrote it down below here because I don't have the answer booklet handy, but that's what you would see. All you're doing is balancing. Now, what I tell my students is we have to make sure whatever we have on the left-hand side is equal to whatever we have on the right-hand side as far as the different elements and the number of atoms of those different elements. You're never going to take anything away. You're always just going to add. Think of it as a seesaw. You want to balance it out. When you have too many on one side, then the other side is up. So we're going to add to the side that's up to bring it back to balance. Let's go ahead, and I just usually move from left to right. I have lithium here on the left. It's represented by lithium hydroxide, only 1 lithium, but on the right here, you see that subscript of 2. I can't change the formula. All I can do is put a 2 in front. All right, so my lithiums now are balanced. We'll move over to oxygen. Now, this lithium, remember, gets distributed throughout the entire formula. So I have 2 oxygens from lithium, and I have 2 from carbon dioxide. That's a total of 4 oxygens. And here on the right, I have 3 from lithium carbonate and 1. So those are equal. 4 and 4, we're good. Let's move to hydrogen. Again, I have 2 hydrogens here from lithium hydroxide because of the 2 in front, and I have 2 here from water, balanced. And finally, for carbon, I have 1 and 1. Just by putting the 2 then in front of lithium hydroxide, we have now our balanced equation. All right, that ends this cluster of questions. We'll move on to the next cluster. All right, for these 3 questions, 71, 72, and 73, I have a reading passage here talking about dissolved ions in water. And question 71, we have to determine parts per million of calcium carbonate, CaCO3, in tap water. Well, just like before, we have the equations on reference table T. This one doesn't come up that often, so let's go and check that out. All right, here we are at reference table T, and we're dealing with parts per million, which is going to be here. Of course, this equation is very similar to percent composition because you have the solute, that's your part, and the mass of solution, that's the solute plus the solvent. So we just have to be aware that sometimes you're given the entire solution or you're given the mass of the solute and the mass of the solvent separate, and you have to add them together here in the denominator. So we just have to be very careful. And also, again, don't forget to multiply. Just like we said with percent composition, you're multiplying by 100. Here you're multiplying by 1,000,000. Well, we need the different masses for solute and solution. And I just drew very not so great here the formula. I would always recommend you do that while you're hunting for your numbers here. With the reading passage, we have a 150 gram sample of this tap water, and it contains 0.00075 grams of calcium carbonate. That tells me then the 150 is the mass of solution, not just the mass of the water. So I'm going to have my 0.00075 divided by my 150 grams times 1,000,000. When you go ahead and plug that into the calculator, what you're going to end up with is 5 parts per million as your answer for question 71. Now, as you're watching this and going through it, if you haven't done the calculations already by pausing the video, calculate it out. Make sure that using the calculator is as important as setting up the questions. All right, we're going to go to 72. All right, in question 72, state in terms of aqueous ions, make sure you have those two words then in your answer, why this tap water can conduct electricity. And it's real simple, all right? Because they're aqueous ions, it means that you have these ions in solution and they can move. So mobile ions in solution is your answer. You have to have moving charges for an electric current. There's two ways in chemistry that comes about. One is just what we said, mobile ions in solution. The other would be with metals, right? With metals, you have metallic bonds and you have mobile electrons. Those are charged as well. You got to have moving charges. All right, I think I've said that enough. We're going to go to question 73 now. There's a picture in, not in, but on the answer booklet that asks you to draw two water molecules. If you just draw one, you're going to have a problem. You can draw more than two, but you can't draw just one water molecule showing the orientation of each water molecule towards the calcium ion. What we're talking about here is they show you the water molecule, literally a circle with two dots. So this is the water molecule that you're given. And you're going to go ahead, you have a calcium ion. Literally, it's just Ca plus 2 in a circle. And you're supposed to line up two water molecules towards the calcium ion. Well, you know opposites attract, right? The oxygen end is more electronegative. That's your negative end of the water molecule. And where your hydrogens are is the positive end. All you have to do is just make sure you orientate two oxygens, the negative end shimmying up to the calcium ion, and maybe I'll just put one over here, again, with the oxygen side of the water molecule closest to the calcium ion. 74 through 77, we have a decomposition reaction of hydrogen peroxide. And in question 74, it says, state evidence from the equation that the reaction is exothermic. Real simple, I look at the equation and you would write down that heat is shown as a product, right? Exo meaning exit, it's leaving the reaction. 75, explain in terms of substances why this reaction is a decomposition reaction. Well, you start with one reactant and now you have two products. It's breaking down, it's decomposing. Again, make sure it says in terms of substances. Don't forget that. If you want to specifically say, hey, hydrogen peroxide is breaking down into water and oxygen, go for it. If you want to just keep it more generic, as I just said, you could do it that way as well. All right, 76, state how increasing the temperature of the hydrogen peroxide affects the rate of reaction. Increasing temperature increases the rate of reaction. Now it says how. Well, how does it increase it? It provides more energy to the molecules of H2O2, and it increases the number of collisions between the H2O2 molecules. It actually is both. So the amount of energy that the molecules possess and the number of collisions, they both go up. All right, for 77, there would be a potential energy diagram on the answer booklet. I'm going to just draw one here. And it says, draw a double-headed arrow to indicate the interval that represents heat of reaction. Heat of reaction is your delta H. That's the amount of energy that's given off. Remember, it's exothermic between your reactants and your products. So this was what you would see on the answer booklet. I'm struggling here a little bit with some of my words. I'm going to change the color. We'll make it green. Right, heat of reaction, again, delta H, the H of the products minus the H of the reactants. In other words, your double-headed arrow is going to be between the products and the reactants. All right, whether you put it here or draw it here or draw it here, that doesn't matter, but it have to be between the products and reactants. Moving on. All right, with this next cluster of questions, we are dealing with a voltaic cell. How do I know that? Because they're the words. Voltaic cell means you have a spontaneous reaction. You're going to have chemical energy that is going to be transformed into electrical energy. It's also easy, if it didn't say voltaic cell, to know it's voltaic because you have two containers here. You have a wire and you have your salt bridge. If you had an electrolytic cell that was shown in the picture, yeah, all right, maybe they might label it, but you will see one container instead of two. So it's just an easy way to go ahead and figure out which one you have. All right, let's move down here. Notice you're also given the net equation here of magnesium and copper ions forming magnesium ions and copper. All right, 78, identify the subatomic particles that flow through the wire. All right, this is something that was probably repeated over and over again in class. You might not remember, but remember, it's electrons that flow through the wire. Now, as a little extra bonus thing, remember the salt bridge. What migrates in the salt bridge are ions. So ions migrate in the salt bridge, electrons move through the wire. 79. All right, for 79, it says compare the number of electrons lost to the number of electrons gained during the reaction in the operating cell. The student might think, oh, I got to go ahead and I got to figure out my half reactions and all. It's not even asking you specifically the number of electrons. It's just asking compare the numbers. The number lost of electrons must be equal to the number gained. So you could just say that they're equal or the same. All right, let's go to the last couple here. 80, state the form of energy that's converted to electrical energy in the operating cell. Well, the form of energy that's converted to electrical energy is chemical energy. You could have said chemical energy or chemical potential energy. All right, all of those would work for 80. For 81, write a balanced half reaction that occurs in the copper half cell when the cell operates. You're pretty much given the answer up here in the overall net equation. Let's pull down copper. So we have copper with a 2+ charge. It's copper ion, and it's going to copper atoms. no charge there. Remember, your oxidation number here is 0. All you have to do is balance out your mass and charge. I have 1 copper on the left, I have 1 on the right. I have an overall 2 plus on the left. That means that this copper ion is gaining 2 electrons and becoming a copper atom. So there is your balance equation. Anytime you're dealing with half reactions and trying to balance equations, if you're given that overall uh, equation, you pretty much just have to bring down what you're focusing in on and then balance out with electrons. And then finally in 82, identify one metal from table J that is more easily oxidized than magnesium. All right, let's go there. Let's check out table J. All right, we find magnesium on table J. Here it is. What you're looking at, the highest is lithium as the most active metal and goes all the way down to the least active. If I'm looking for something that is more active or reactive than magnesium, it's going to be any of these metals above. Real simple. You could have picked any of those and the answer would be correct. And what does that mean? Metals, remember, are losers. They want to lose electrons. While magnesium wants to lose its 2 valence electrons, again, anything above it wants to lose them even more. All right, before we get to the last few questions, I just wanted to point out that the June 2022 Regents exam was a typical Regents exam. Part C here, remember I said this is the last section. You're tired, you got 20 questions here, you got to fill in the answers. Some students of mine decided that this was the first part they were going to do when they took the test as opposed to the last. What I just wanted to point out here is electrochemistry, which is not easy for students. Notice they have it here at the very end of the test, along with this last group now of questions, that's nuclear chemistry. Again, it's typical of the writers of this exam to put these 2 units towards the end. And there's a half-life question here, which some students struggle with. And I don't know, I'm just pointing it out to you that you might want to tackle this first as opposed to last when you take the test. All right, let's get these last 3 in here. We have an element, 117, and it's being synthesized. And we're getting this other element and 4 neutrons out. We're given also the half-life as 320 days, which decays by beta emission and also emits energy as gamma rays. For 83, determine the fraction of this BK249 that remains unchanged after 970 days. I don't know where I got the 1 from. What I like to have my students do is a chart, mass, and time. I'm just going to put a T. After 960 days means what is left after 960. I'll put that at the bottom. We're starting at time 0. So that would be as if I click on a stopwatch right now, we go out 960 days. Because it's asking about the fraction that remains, we don't have a mass to start with. Instead, we're going to start with 1. And then we're going to just go ahead and get fractions from there. Now, with our mass, when we hit every half-life, what that means is half of those atoms of BK249 have now transformed into a different isotope, and 320 days would have gone by. So we started with the whole thing. When we have half still as BK249, I'm at 320 days. So I'm having my mass and I'm just adding time. Well, the next half-life that we hit is going to be another 320 days. So 320 plus 320, which is 640. And now we're at a quarter. And now I'm going to add another 320. And now we're at 960. And half of a quarter is 1/8. And that is our answer. To keep track of this, what I would recommend is not only setting up the chart, but use your calculator. And each time you half the mass, just add the next half-life in the calculator, and in this case until you get to the 960. Let's move on. In 84, state in terms of both protons and neutrons. Why these two are isotopes of the same element, same number of protons, different number of neutrons. And on the answer key, if you wanted to use the actual numbers, both the UUS 293 and the UUS 294 contain 117 protons, and then the 293, 177 neutrons. I'm sorry. Yeah, the 294 is 177 neutrons, and the 293 would be 176. But literally, what you're dealing with here is the definition of an isotope. Same number of protons, different number of neutrons. Finally, we are at the end here in question 85. Complete the nuclear equation in the answer booklet for the alpha decay of the UUS 294 by writing a notation for the missing product. I'm going to write it below, and then we'll go ahead and put that in. You're given the equation for the alpha decay as follows. You're given the UUS with the 294 and the 117 written on the answer booklet. You're given the helium nucleus, which is your alpha particle of 4 and 2, and then you're filling in what I already filled in here for the missing product. Let's just go over it. When you're balancing out nuclear equations, the mass numbers must be equal on both sides of the equation and the atomic numbers. You started with 294. On the right-hand side, you have a 4, and then you have to add 4 to the number to get 294, so it's 290 plus 4 equals 294. So 290 is the mass. And then for the atomic number, we started with 117 on the left. On the right, we had 2. Well, what number plus 2 equals 217? That's 115. That atomic number, remember, that's the atom social security number. It also then gives you the identity of the element, which you would look up on the periodic table, which is listed on the Regents reference table as capital U and then lowercase u and a P. That's it. Part C, done. Just keep working hard. I hope that you check out some more videos. Good luck. Thanks for watching.